In this video, we're going to apply our method of Lagrange multipliers again, but to a new example. We're going to consider the points on the curve x to the fourth plus y to the fourth equals 1, and that almost looks like a circle, and in fact it is like a circle in rough shape. If we had x squared plus y squared equals 1, we would get a perfectly uniform circle. The x to the fourth, y to the fourth, the effect that has is to sort of square off the circle. We go a bit further out, and it ends up looking a bit like this. X to the fourth plus y to the fourth equals 1. And our goal is to find the points on that curve that are closest to and furthest from the origin, so in the center here. We can pretty quickly see what those points are just from a sketch of the image here. The closest points will be these ones here along the axis, and the furthest out we can get are going to be in the corners, but we should also be able to validate that with our Lagrange multiplier calculations. To achieve that, we have to express our f as a function of what we want to optimize. Goal is to optimize the distance to the origin. And so our function of x and y is going to equal distances, x squared plus y squared. In fact, let's put it more formally here. The distance between x and a 0 point, and the distance between y and the 0 point, that captures the distance in x and y. We square it. And then usually we would square root it. That would be the official distance. But we've seen this before as well, where we can look at the distance squared, and what that does is get rid of our square root in our calculations here. And the points that are the closest distance will also have the closest distance squared. And likewise, the points that are furthest in distance will have the furthest distance squared. And the reason we like doing that is because it makes our function a lot simpler to work with. There's no square roots. That makes any differentiation a lot easier. The second ingredient here is our constraint. That whole thing is our constraint, and it comes with two pieces, our g of xy, and the k value here would be 1, the value that's on the right hand side naturally. We're now prepared to build our Lagrange multiplier equations. Remembering that the two main ingredients are the x derivative in f and g, and the y derivative in f and g. And the idea is that they are equal to each other except with a multiplier lambda in between. And then the constraint itself comes down, x to the fourth plus y to the fourth equals 1 is our third equation. We then fill in the blanks with our formula. This is good to go, but our x function, but our f function, we need the x derivative of that. We scan this function here, we simply get 2x. We have the lambda, then gx. Where's g? G's up here. It will be 4x cubed. Then we do the same thing for the y derivative of f. Here's f. Take the y derivative. There are a lot of moving pieces here, so be careful. That equals lambda times the y derivative of g. We look up for g, here's g. The y derivative will be 4y cubed. And then we copy down our constraint. We can then label those equations 1, 2, and 3, and start to solve and see what we can do. Now we need to be able to solve for these various forms, so let us take equation 1 and see what we can do with it. Because we have multiple x's and it's dangerous to divide through by variables, it's nicer to be able to put this in factored form. So what we're going to do is bring this to the other side. 2x minus 4 lambda x cubed equals 0. And then what we're going to do is factor. There's a common x. We can have the 2 there as well. Then we'll have 1 minus 2 lambda x squareds equals 0. And with that form, we get x equals 0, or move that over for some space, or we have 1 minus 2 lambda x squareds equals 0. What that will do is let us solve for lambda that we can then use in one of the other equations. So if lambda is what we're solving for, We can bring this over to the other side, so we end up with 1, and then we divide through by the 2x squared. So we have two possibilities out of that equation, either x equals 0 or lambda is equal to 1 over 2x squared. We can do a similar transformation for equation 2. If we bring all these terms to the other side, we're going to have 2y's. Bring this over, minus 4 lambda y cubed equals 0, and we can factor that as well. Every term has a 2y, and then we brought a 2 out, so we'll have 2 lambda. We brought out a y, we'll have a y squared equals 0, and in exactly the same form here, we'll have y equals 0 from this term, or this calculation, which gives us another lambda possibility, 1 over 2y squared. Now we have a chain of possibilities to investigate. We'll continue this on the next page. If x equals 0, that's one possibility, then we can sub that into our constraint over here, and that gives us x equals 0, means 0 to the 4 for that term, and we can solve that for y to the 4 equals 1, or y equals, if we take the fourth root, that gives us plus or minus possibilities, and plus or minus 1 will be the option there. And so 0, 1, or 0, negative 1. We can also take our y equals 0 value and do the same thing with our constraint. This is note equation 3 here. And then we get x to the 4th plus y to the 4th, but y is now 0, equals 1. And this time it's x to the power 4 equals 1, or x equals 1 plus or minus. And that gives us 1, 0, or negative 1, 0 as possibilities. Going back to the last combination of equations back here, we have two lambda values that also must be equal to each other. So we're going to set those equal and see what they tell us about x and y. So let's call this 4 and 5. And if we set 4 equal to 5, we're going to have 1 over 2x squared equals 1 over 2y squared. Cross multiplying here, we're going to have 2y squared equals 2x squared. That's y squared equals x squared. And you got to be careful with the square roots here. If we take the roots of both sides, we could get a positive or negative version of x. So positive x or negative x. And then we take that and put it into 3. So if y is equal to positive x, put that into 3, which is our constraint equation here. If y and x are the same, we'll have x to the 4 plus x to the 4 equals 1. That's 2x to the 4 equals 1. X to the 4 equals a half. And x is equal to plus or minus the fourth root of 1/2. And with that, we had y equals x. So that's going to give us 2 points. Negative the fourth root of a half, that's x, and y is the same, negative fourth root of a half, or the positive root, fourth root of 1/2 and fourth root of 1/2. Last but not least, we have y equals negative x. Sub that into 3, we're going to see something almost the same, because we'll have x to the 4 plus negative x all to the power 4 equals 1. When we take the fourth power, the sign disappears. When we take the fourth power, the sign disappears. So we actually end up with exactly the same equation we did before, and that's going to give us the same solutions. Positive this fourth root of 1/2, and negative the fourth root of 1/2. Those are going to turn into, careful with this, when we have the positive x, we're going to get a negative y value. So we're going to mix and match the signs this time. Fourth root of 1/2. And if we take the negative x, fourth root of 1/2, then that's going to go with a positive version when we talk about the matching y coordinate. All right, so that gives us a collection of 1, 2, 3, 4, 5, 6, 7, 8 solutions, or 8 points from the Lagrange multiplier equation. So we have an abundance of riches here. Now the question is, which value or which locations give us the highest value for the function or the lowest value? Let's go back a page just to see what's going on. We want to find the points that are closest to and furthest from the origin. So that comes back to evaluating our function at all those points. How far are those away? Well, our function is, our squared distance function, is simply x squared plus y squared. And if we look at all the points that we have that look like these values here, and we calculate f, this will be 1 squared plus 0 squared, that'll be 1. This will be 0, oh, hey, we start to see the same value over and over and over again here. And then we can do the same thing for our negative 4th root of a half. Let's do the double negative first, and then we'll go flip the signs. Same values, and positive. Same 4th root of a half for all of these. When we calculate the function value, x squared plus y squared there, we're going to get the negative going away because we're squaring it, and the 4th root, when we square it, turns into a square root. So we'll have the square root of a half plus another square root of a half, and that's going to give us 2 over root 2 if we like. That's an easier way to express that. And if we do the same thing for the values that are positive and negative, well, we're going to plug them into the square term, so whether it's positive or negative doesn't matter. We're still going to get the square root of a half plus the square root of a half. That's going to be 2 over root 2. Hey, they're all going to be the same. So the function values at all these points has the same numeric value, and this is going to be larger than 1. So these are the smallest possible f values, and that translates to the closest points to the origin. That was our function. It measured the distance squared to the origin, and these points here are all the largest f values, and those translate then to the furthest points from the origin. And we can do a quick confirmation of that on the next page, looking at the contour diagrams. On this graph we have here x to the 4 plus y to the 4 equals 1. That's that squared off circle idea. And then here we have the contours of f. And the contours of f represent the distance to the origin. Then we can see clearly that all the points on a circle have the same distance to the origin. We've put them here irregularly spaced just so they'll match the contours or line up with the constraint. We haven't done an even spacing on the red lines here just because we want to be able to match them up exactly to the constraint value here, the constraint graph. Again, taking your imagination and viewing this as a view from above of a surface, and this is a road that we're allowed to drive on. We have to stay on this road. Then we can imagine as we drive around this road, we're going to be crossing contours, we're going to be going to different heights, and in fact, this height here, this contour at the inside is labeled 1, and this outside one is the height of 1 over root 2. And so what we'd see is that this is low values getting bigger and bigger and bigger. So it's uphill as we go out from the center. So we imagine driving along the road, and as we're driving this way, we're going uphill and uphill and uphill, and then the road hits its highest point at this location here. Well, that's the furthest away from the origin we can get. But as the road curves, we then turn down, we start going downhill and downhill and downhill, and we get to this point here, we're at the bottom. We're at the lowest possible point because we're closest to the origin. And then after that, we go up and we just alternate here our maximum and minimum values as we go around the circle. So the 4 points that we found in blue are exactly the 4 points that we found here that were all distance 1 squared away from the origin. And all the red dots are the matching root 2 or fourth root of 1/2 values that we found that were furthest away from the origin. And again, we can see at the points of interest, if we drew perpendicular lines to both contours and to constraint, they would point in the same direction, and they wouldn't anywhere else. So those 8 points are special, and they satisfy that particular Lagrange multiplier equation set, or the parallel gradient configuration, when we look at it as a contour diagram. Again, a nice jigsaw interlocking way to look at both a picture and, going back to our source equations here, the Lagrange multiplier equations that reflect the same ideas, only in formulas.